Welcome to my lesson on the Pythagorean Theorem and its converse. Most of you probably remember the Pythagorean Theorem is a squared plus b squared equals c squared. We're also going to talk about the converse of the Pythagorean Theorem in the second half of this lesson. I'm going to break this lesson into two parts because it's kind of long. And in that second part, we're going to cover the converse, which is something that perhaps you haven't seen. Some new vocabulary here. Pythagorean triple, you may have seen this, you may not have, but a Pythagorean triple is a set of three natural numbers, a, b, and c, that satisfy the Pythagorean theorem. A squared plus b squared equals c squared. Now, natural numbers, another way you might hear this is positive integers. Positive integers are basically natural numbers. And here's our Pythagorean theorem, in case you've forgotten. And in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. So if you haven't heard this term in a while, hypotenuse is the longest side in a right triangle. It's always located across the triangle from the right angle. So the only way you can really get into trouble with the Pythagorean theorem is if you forget that c, the hypotenuse, must be by itself on one side of the equation. A squared and b squared can be interchanged because addition is commutative, but you've got to remember that c has got to go by itself on the right side of the equation. If you can remember that, you can always find the missing side of a right triangle if you have two of the sides. And at the beginning of this class, we learned about the distance formula, and we learned that it was derived from Pythagorean theorem. And before we went ahead and used that, we went and did a proof of the Pythagorean theorem. This is kind of interesting because there's lots of different ways you can prove the Pythagorean theorem. And now that we've done similar triangles and geometric mean, we have a new method that we could use to prove the Pythagorean theorem. Let's try it here. If we're given triangle ABC with right angle at C, they want us to prove that a squared plus b squared equals c squared. So one thing we can do is draw this altitude, CD. And since ABC is a right triangle, we know that that's going to split this triangle into three similar triangles. So one thing that we could recognize, if we're after a squared plus b squared equals c squared, you might remember what we talked about geometric mean or geometric means. And we know that this a is always going to equal the geometric mean between y and c. Or we might say that a over y hypotenuse over short leg will equal c over a hypotenuse over short leg. So a over y equals c over a. And your cross products there are going to give you a squared equals c times y. I did it that way because I want to end up with an a squared, because that's what we're after. That's what we're trying to prove. So we could do the same thing here. We know that b is going to equal the square root of x times c, the geometric mean between x and c. Or we could go back and set that up as a proportion. In this medium triangle, hypotenuse over long leg, b over x, equals, in the larger triangle, hypotenuse over long leg, c over b. And your cross products there are going to be b squared equals c times x. Good. If we add those two together, we're going to get a squared plus b squared equals cy plus cx. Okay. And where could we take this from there? So if we want to find c squared, you might notice that c here equals y plus x. So we could go ahead and factor out a c from both of these terms. We'd end up with c times y plus x. If you're paying attention, you might notice that we have a substitution here that we could do. We could rewrite that as a squared plus b squared equals c times c, or a squared plus b squared equals c squared. So just another interesting way to prove the Pythagorean theorem and show that all of this stuff really fits together well and proves itself. Let's try a couple of examples. Here's an example. I want us to find x. Now, the only way you can really make a mistake with the Pythagorean theorem is if you get c in the wrong place. In this particular problem, x equals c. So we want to do 4 squared plus 7 squared equals c squared, or x squared. And we'll get 16 plus 49 equals c squared. And when you add those together, you get 65 equals c squared. If you take the square root of both sides, you'll get c equals, or x equals, the square root of 65. All right, let's try another one. Again, here, just make sure you get c in the right place. In this particular case, 12 is c. So when you write the Pythagorean theorem, a squared plus b squared equals c squared, you should get something like this. And we'll get x squared plus 64 equals, that's just 12. 12 squared is 144. That's gross. And we can subtract 64 from both sides. We get x squared equals 80. And if we take the square root of both sides, we're going to get x equals, we can factor that into the square root of 16 times 5. So we get square root of 16 times the square root of 5, which is 4 square roots of 5. Let's try another one. Here, they want us to find x. This time, x is the hypotenuse. So we know x is going to go by itself on one side of the equation. X squared equals 5 squared plus 8 squared. So we're going to get x squared equals 25 plus 64. And 25 plus 64 gives us 89. And we can take the square root of both sides and get x equals the square root of 89. And that's a perfectly good number. Don't feel the need to put it in your calculator and turn it into an irrational number and round it and make it an exact. That's an exact answer, and it's perfectly acceptable. All right, next problem. Here, this time x represents either a or b, and 12 is the hypotenuse. So we want 12 by itself on one side of the equation. 12 squared equals x squared plus 6 squared. And we can solve this for x. 12 squared is 144. Yes, that's gross. And 6 squared is 36. We can subtract 36 from both sides. And we get, what do we get when we do that? 108 equals x squared. And when we take the square root of both sides, we get the square root of 108. I think we can factor that into the square root of 9 times 12 equals x. We can further factor that, square root of 12. We can factor that into square root of 4 times 3. So we get 3 times 2 times the square root of 3 equals x. Or 6 square roots of 3. Okay. Let's take a look at some Pythagorean triples. Some of the common Pythagorean triples you're going to see are 3, 4, 5. These satisfy the Pythagorean theorem. Notice we can plug these in. We get 3 squared plus 4 squared equals 5 squared, or 9 plus 16 equals 25. And so these are natural numbers that satisfy the Pythagorean theorem. And notice, if you've got one Pythagorean triple, you can multiply all of them by 2 to get another set of Pythagorean triples. You can multiply them all by 3 to get another set. Here's another common Pythagorean triple: 5, 12, 13, 8, 15, 17, and 7, 24, 25. If you forget your Pythagorean triples, this is not something you have to memorize. If you forget your Pythagorean triples, as long as you haven't forgotten the Pythagorean theorem, you can still solve for whatever it is you're looking for in your right triangle. One interesting application for Pythagorean triples is when you're working with construction elements that are of fixed length. Then you may want to know some of these triples so that you can arrange brackets in 90-degree angles. These are Legos, and it's interesting, you can count 4 spaces on your Lego brackets: 4, 5, and 6. Now you might say, hold on, that's not a Pythagorean triple. But really what we're talking about is the distance between the centers of those holes. The distance between these here is 1, 2, 3 spaces, 1, 2, 3, 4 spaces, and that fits perfectly with a hypotenuse of 1, 2, 3, 4, 5 spaces. So if you take a Pythagorean triple and you add 1 to each number, you can then use it to put together, for instance, Legos, and always end up with a perfect 90-degree angle. Here, could we use a Pythagorean triple to find x? Well, if you forgot your Pythagorean triples, you can always go back to the Pythagorean theorem, but you might recognize these guys. If you divide these by 2, this is 12, and this is 13, and you get x would be 5. So in this case, x would equal 10. It's a multiple of that 5, 12, 13 triple. 10, 24, 26. If you remember the Pythagorean triples, they save you time. If you forget them, don't panic. Just use the Pythagorean theorem. Here, could we use the Pythagorean triple to find x? You might recognize this as another multiple of 5, 12, 13. If you said x is 15, you'd be right. This is basically 3 times 5, 3 times 12, and 3 times 13. If you forget, no problem. X squared plus 36 squared equals 39 squared. And you can crank that out, and you're going to get the right answer. Let's try a word problem. Here we have a 20-foot ladder placed against a building to reach a window that is 16 feet above the ground. How many feet away from the building is the bottom of the ladder? If they didn't give it to you in this problem, if you have to sketch it yourself, you can make an assumption. If we've built the wall correctly, then that should be a right angle. And when you have a right angle, then you get to use Pythagorean theorem. So you might have recognized that in this particular case, the ladder represents the hypotenuse. So we'll put that by itself on one side of the equation. And that should equal x squared plus 16 squared. So we get 400 equals x squared plus 256. We can subtract 256 from both sides. And it's almost as if I designed it this way so that the answer would be 144. That's gross. Equals x squared. Can we take the square root of both sides? Yep. And we'll get 12 equals x. Okay. That is the first part of my lesson on Pythagorean theorem. Don't forget to watch the second part. The second part is going to be on the converse of the Pythagorean theorem. which will probably include a few things that perhaps you haven't encountered before.